All right, hello guys. It's been a while, and today I just wanted to look at the integrated rate laws in chemical kinetics. And first of all, you might be wondering, what is the use of these integrated laws when we have our differential form? And well, speaking of the differential form, it might be nice to just clarify what the notation means if you're unfamiliar. Well, firstly, for the zeroth order, we usually express as a rate is equal to k, the rate constant. But rate in mathematical terms is really the derivative. And then remember that the concentration decreases, so we can say that it is a negative derivative since there's a negative rate of change. So simply, the negative rate of change of concentration with respect to time is k. And for first order, we have a concentration term, and then second order, we have the concentration time term squared. And that's why it's called second order. And now we can start off uh, talking about why we need the laws. Well, first of all, having the integrated rate laws allow us to identify what order our reaction will be simply by looking at the first, you can tell by looking at the concentration versus time graphs, or you can also tell by looking at the linearized graph, whether it's linearized using the natural logarithm or linearized using the reciprocal 1 over concentration. You can tell whether something is first order, zeroth order, or second order just by looking at the shape of the graph. And secondly, we can find the rate constant easily with the integrated rate laws just by looking at the slope of the linearized graph. And lastly, or maybe some might say it's the most important one, we realize that we have an expression for time, or we have an expression in terms of time, and this allows us to solve for time in our reactions, which is extremely valuable. All right, now let's get started. So first of all, in our zeroth order, we can just separate our variables. So negative dA is equal to k dt. I just move dt to the other side. And then the integral of dA is equal to the integral of negative k times the integral of dt. So now we want to pick our bounds. And well, what bounds should we use? We can just use from 0 to a certain point in time, which we can just express as t. Well, from 0 to t. And what would the according bounds be for concentration? Well, at time 0, the concentration, we just know it's A naught. And then at time t, you can either say the concentration is concentration sub t. I'm just going to leave it as is because, we can just understand in the context that that's what it means. Of course, for your own clarity, you can do that. And now, simply, this integral is, fairly easy to do. The concentration minus the initial concentration is equal to negative kt. All right. And now we want to, for all these expressions, we want to rearrange to have the concentration at one side separate from the initial concentration. And this gives us that the concentration is equal to the initial concentration minus kt. And that is the integrated rate law for a zeroth order reaction. And now we can move on to the first order reaction, similarly enough, but just this time it's a bit different because we have a concentration term on the right. So we can move that over. So we get dA multiplied by 1 over A is equal to k dt, or we can also move this negative sign over just to make it easier. And integrating this, again, from 0 to time, is A naught, and A, we're integrating, just to make it easier, we're integrating 1 over concentration dA. So I'm just saying A here, but really, remember, this is an expression for concentration. It's just kind of a mouthful to say concentration every time. On the other side, we have the integral from 0 to t of negative k dt. So I just wrote it like this just to make sure you know that we're taking out the constants like earlier. Just because they're constants, you can take it out of the integral. And then what's the integral of 1 over x? Well, remember, this is a special case and we can't use the reverse power rule. It's just a result you have to know. And the integral of 1 over x is ln x. So over here, the integral of 1 over a would be ln a. Remember, we have bounds. So we would have ln a minus ln a naught. And the other side is, again, negative kt. We can combine this into a single logarithm using log laws, and that tells us uh, the natural logarithm of a over a naught, just in one term, so it's easier. And we want to isolate a again. Well, we can raise e to the power of everything on both sides to get rid of the natural log, and this gives us e to the natural log cancels out, so a is equal to a naught times e to the negative kt. So I just raised it and then moved a naught to the other side, and that's our expression for the first order integrated rate law. And now finally, or just where I'm going to be talking to for today's video, the second order reaction. Now the second order reaction, uh, it's the same thing. We separate our variables. So this time it's a squared because the second order reaction, and the other side is negative k dt. So the integral from a naught to a of uh, 1 over 1 over a squared dA is equal to negative k times the integral from 0 to time of time, or with respect to time. And now, integrating this, remember the integral of 1 over x squared is negative 1 over x. So now remember the integral of 1 over x squared is just negative 1 over x using the reverse power rule. And we can just write this down slowly to not make any mistakes. So negative 1 over a minus negative 1 over a naught. So that's our left side, and the right side is again negative kt. So negative 1 over a plus 1 over a naught is equal to negative kt. We can rearrange again. We first of all multiply by negative 1 to get rid of the negatives. So we get 1 over a plus 1 over, or sorry, minus 1 over a naught is equal to kt. So this integrated law, it's sufficient to leave it as, or we can go one more step. So 1 over a is equal to 1 over a naught plus kt.